In section 3.5, you will learn about limits at infinity and horizontal asymptotes. So in part 1 here, we're going to discuss how limits at infinity are used to find horizontal asymptotes. So taking a limit at infinity means we let x go to infinity in the limit, and in this case, the function we're going to look at is the reciprocal function, 1 over x. So if we plug that infinity in, we would get 1 over infinity. And of course, you know that as the denominator of a fraction gets bigger and bigger and bigger, the fraction itself gets smaller and smaller and smaller. So if the denominator goes to infinity, then the fraction is going to go through 0. And that's going to be true whether the limit goes to positive infinity or the limit goes to negative infinity, because 1 divided by negative infinity is also 0. So if you let c be any constant real number and let the exponent n be positive, then the limit as x goes to infinity of c over x to the n means we are taking c divided by infinity to the nth power, and no matter how big c is, infinity always wins. Infinity is infinitely gigantic versus any constant you may have in the numerator, so this will go to 0. So if we apply that now to this example right here, we have the limit as x goes to infinity of 4 billion over x squared. So we've got 4 billion over infinity squared. Well, that's just applying this rule right here. No matter how big your numerator is, 4 billion is literally nothing compared to infinity, much less infinity squared. So this is going to go to 0. Now this brings us to our definition of horizontal asymptotes here. And the line y equals L is a horizontal asymptote of f of x if either of the following limits is true. If the limit as x goes to infinity of f of x is L, or the limit as x goes to negative infinity of f of x is L. So let's look at this next example to help you understand how this works. Looking at this graph here, if we were to do the limit as x goes to negative infinity of f of x, we can see on this graph, as x goes towards negative infinity, the y value is just getting closer and closer and closer to y equals 3. So that means the limit as x goes to negative infinity of f of x is equal to 3. Because we had a limit at negative infinity of the function equaling a real number, then that means there is a horizontal asymptote at y equals 3. Now if we compare that to the limit as x goes to positive infinity of f of x, we look at the graph, and as x goes towards infinity, y is going towards negative 3. So that limit equals negative 3. Therefore, there's a horizontal asymptote at y equals -3. So if we review what physically is happening on the graph here, we see as x approaches -infinity, y approaches 3. That's what's happening in this direction. Whereas over here, as x goes to positive infinity, y goes to -3. So those behaviors on the graph lead us to be able to find these limits, and then because of the definition of horizontal asymptote, that's how we prove that these horizontal asymptotes exist. Next up, we want to evaluate the limit as x goes to infinity of the quantity -8 plus 5 over x. Now remember your limit properties. The limit of a sum can be written as the sum of the limits. So this becomes limit as x goes to infinity of -8. Notice I have to put parentheses around the -8, plus the limit as x goes to infinity of 5 over x. We know the limit at any x value of a constant function is just the constant, and the limit as x goes to infinity of 5 over x, that's going to go to 0 because 5 over infinity is 0. So this limit is -8. Now what this means if you have a limit at infinity and that limit equals a real number, then applying the definition of horizontal asymptote means that this function f of x equals -8 plus 5 over x has a horizontal asymptote at y equals -8. Next up, we have to evaluate the limit as x goes to -infinity of the quantity 2 plus sine of x over x squared. Now I'm going to do my evaluation over here because we're going to have to do a bunch of side work over here. So this will equal the limit as x goes to -infinity of 2 plus the limit as x goes to -infinity of sine of x over x squared. Now we know this first limit, because this is a constant, is just going to be that constant, 2, plus, now this limit, we don't know how to evaluate it because the numerator is not a constant. Remember, the rule that we have is if we do the limit at infinity of a constant over x to the n. But since sine of x is not a constant, that rule does not apply. Let's go off on the side here. The range of sine of x is from -1 to 1. We can say that -1 is less than or equal to sine of x is less than or equal to 1. Now we are interested in evaluating this function, So we see that we can get there if we divide each of the terms by x squared. Now we know that x squared is a positive number, can't be 0 because it's in the denominator. So we know x squared is a positive number, so our inequality symbols will remain unaffected. So we have negative 1 over x squared is less than or equal to sine of x over x squared is less than or equal to 1 over x squared. We just divided everyone by the same quantity. So now we have this argument, and what we want to do is put the operation of this limit on all three pieces. So we will do the limit as x goes to negative infinity of negative 1 over x squared will be less than or equal to the limit as x goes to negative infinity of sine of x over x squared, which is less than or equal to the limit as x goes to negative infinity of 1 over x squared. Now we can evaluate each of these limits separately. The limit as x goes to negative infinity of negative 1 over x squared. Now here we can apply that rule. We have a constant over infinity that's going to 0. Inside we have limit x goes to negative infinity sine x over x squared less than or equal to, over here we have limit x goes to negative infinity of 1, which is a constant, over x squared, which is like x to the n. This is also going to 0. So therefore, by the squeeze theorem, we know that the limit as x goes to negative infinity of sine of x over x squared will have to be 0. And we can take that and fill it in over here. And now that means this original limit works out to be 2. In this example, we have to compute each limit to determine if the function has a horizontal asymptote or not. So looking at this first limit, we see we have the limit as x goes to infinity of the quantity 9x plus 7 over the quantity 3x minus 6. Now if we just tried direct substitution, we see that we would get infinity over infinity. And just like 0 over 0, infinity over infinity is undefined. And that tells you you are going to have to do something else. Now, the technique for solving limits like this when you get infinity over infinity is to multiply by 1 in the form of, in this case, 1 over x over 1 over x. So because this exponent of x was x to the 1, I'm going to multiply by 1 in the form of 1 over x to the 1. So now this is going to work out to be the limit as x goes to infinity. Remember that this 1 over x in the numerator will distribute to both of these terms here. So when we take 1 over x times 9x, we will get 9. And then we have a plus sign. And then we have to take 1 over x and multiply it times 7. So that becomes 7 over x. In the denominator, we have to do the same thing, and we have to distribute that 1 over x times the entire denominator. So 1 over x times 3x is going to be 3, and then we have minus 1 over x times 6 will be 6 over x. Now, using the rule that we know about limits at infinity of having a constant over x, we know when we apply that limit that this is going to go to 0. And the limit as x goes to infinity of 6 over x will also go to 0. So now all we have left is this constant of 9 over 3, which of course we know equals 3. And because the limit as x goes to infinity of the function equaled a real number, we say therefore there is a horizontal asymptote at y equals 3. Now let's compare that to this next example where we have the limit as x goes to infinity of the quantity 3x squared plus 2 over 6x squared minus 5. Once again, if we tried direct substitution, we would get infinity over infinity, which is undefined. So we are going to multiply by 1 this time in the form of 1 over x squared over 1 over x squared. This is going to equal the limit as x goes to infinity. Remember, we have to distribute this numerator. So 1 over x squared times 3x squared is going to be 3 plus 1 over x squared times 2 is 2 over x squared. When we distribute in the denominator, 1 over x squared times 6x squared is 6 minus 1 over x squared times 5 is 5 over x squared. And you can see why we like to use this technique, because now we can go ahead and perform this limit at infinity. We know that 2 over x squared is going to go to 0, and so will 5 over x squared. So this will just work out to be 3 over 6, which equals 1/2. Because the limit at infinity of the function equaled a real number, therefore there's a horizontal asymptote at y equals 1/2. In this next example, we have the limit as x goes to infinity of 3x plus 2 over 6x squared minus 5. So for the first time, the exponents are different, and you will have to decide what form of 1 to use. And the recommendation is always use the biggest exponent that appears in the denominator. So we're going to multiply by 1 in the form of 1 over x squared over 1 over x squared Now we've got limit x goes to infinity, we have to distribute. We know 1 over x squared times 3x would be 3 over x plus 1 over x squared times 2 is 2 over x squared. In the denominator, we have to multiply using distribution. 1 over x squared times 6x squared is 6 minus 1 over x squared times 5 is 5 over x squared. Now we can apply the property that as the limit as x goes to infinity of any constant over x to the n has to be 0 to say that 3 over x is going to go to 0, 2 over x squared is going to go to 0, and 5 over x squared is going to go to 0. So we get that this is going to equal 0 over 6, which is 0. Therefore, there's a horizontal asymptote at y equals 0. Now in this last example, we have the limit as x goes to infinity of 3x squared plus 2 over 6x minus 5. So we're going to multiply by 1, and remember the recommendation is use the largest exponent that appears in the denominator. So we're going to multiply by 1 over x over 1 over x. Now this is going to equal limit as x goes to infinity 1 over x times 3x squared is going to be 3x plus 1 over x times 2 is 2 over x. In the denominator, we have to take 1 over x times 6x, which is 6, minus 1 over x times 5, which is 5 over x. Now let's go ahead and apply the limit as x goes to infinity. We see 2 over x is going to go to 0, 5 over x is going to go to 0. Now of course 3 times infinity is infinity in the numerator. We have a 6 in the denominator, and infinity divided by 6 is infinity. So in this case, because the limit as x approaches infinity of the function did not equal a real number, therefore there's no horizontal asymptote. Remember that that definition is that the limit at infinity has to end up equaling a real number, meaning a finite value. That's what will give you the horizontal asymptote. If you don't get a finite value for the limit, then you do not have a horizontal asymptote. Here we have to use the previous example to summarize when a rational function will have a horizontal asymptote. Now, as we review the previous limits, we notice that whenever the degree of the numerator and the degree of the denominator were the same, we ended up getting a horizontal asymptote. It also worked out that if the degree of the numerator was less than the degree of the denominator, we also got a horizontal asymptote at 0. But if the degree of the numerator was greater than the degree of the denominator, then we did not get a horizontal asymptote. So horizontal asymptotes will occur when the degree of the numerator is less than or equal to the degree of the denominator. But remember, to prove that you have a horizontal asymptote, you must use that definition, which involves using a limit at infinity. In part 2, we will be evaluating limits at infinity involving square roots. A quick algebra review. We know that the square root of x squared is defined to be the absolute value of x, and the absolute value of x is defined to be this piecewise defined function, where if x is negative, we have to take the opposite of x to get its absolute value, because taking the opposite of a negative number is what turns it positive. Whereas if x is greater than or equal to 0, then the absolute value of x is just x. Let's explore this definition. Looking at this example, we have to take the square root of the quantity -3 squared. Well, using this definition, we know that we are going to take the absolute value of our x value. And now here, x is -3. So we are taking the absolute value of -3. Now, applying the piecewise definition, because our value for x is negative, we're using this top part of the definition, and the absolute value of -3 will then have to be the opposite of our x value, which is -3, and the opposite of -3 is 3. So what you want to do is make sure that you understand how this definition gets applied, and we did that looking at a concrete example with a finite number here. Now what we're going to do is explore this inside of a limit. In this example, we have to compute each limit to determine if the function has a horizontal asymptote or not. Here, we have to find the limit as x goes to infinity of the quantity 12x minus 5 over square root of 9x squared plus 1. Now, if we tried direct substitution and put infinity into x in the numerator, then we would have infinity in the numerator. And if we put infinity into x in the denominator, we would also have infinity. We know that this is indeterminate, which tells us we're going to need to do some algebra first and simplify this into something that we can find the limit of. Now, from our previous examples, we know that we want to multiply by 1 using the largest exponent in the denominator. Now, when you look at this denominator, you have to realize that it's not a degree 2 polynomial in the denominator because it's the square root of x squared in the denominator. So the effective degree, if you will, is actually 1. So we do expect that there will be a horizontal asymptote because the degree of the numerator is 1. The effective degree of the denominator is 1. And when the numerator and denominator have the same degree, we do expect that there will be a horizontal asymptote. Now what we want to do is multiply by 1 using the following form. And I'm purposely making this line kind of long here. In the denominator, we're going to treat this as 1 over the square root of x squared. So then that means we have to write the same thing in the numerator. We're going to come back and write some other things here, but for now, let's put equals the limit as x goes to infinity, make our fraction bar. Now, in the denominator, we have this expression, which is under a radical, and we have this expression in the denominator of the denominator, which is also under a radical. So let's add a little something to your algebra review here and say that when we have the square root of a times 1 over the square root of b, then that's just a single square root of a over b. And we can apply that in this denominator here because we have the square root of 9x squared plus 1 over the square root of x squared, so we can write that as a single square root and distribute 1 over x squared times 9x squared is going to be 9. 1 over x squared times 1 is 1 over x squared. They're both under the radical, so you could think of this as the square root of 9x squared plus 1 over x squared, and then we take that and split it into this. Now, in the numerator, we have a problem because this is under a radical, but this is not. And what we're going to do is use this definition to help us get the square root of x squared out from under the radical. So we know that the square root of x squared is just the absolute value of x. And remember, this is in the denominator, so this is in the denominator. Now we have to decide whether we're going to write it as negative x or x, and that is based on whether x is negative or x is greater than or equal to 0. Because our x is going to positive infinity, that tells us that x is positive, and we're going to be able to write absolute value of x as just plain old x. Now, when we distribute in the numerator, we are going to use this form to multiply each of those two terms when we do distribution. So the numerator becomes 1 over x times 12x, which is 12. Then we have that minus sign, and we have to do 1 over x times 5, which is 5 over x. Now we are ready to go ahead and apply the limit as x goes to infinity. We know that means 5 over x is going to go to 0. 1 over x squared is going to go to 0. We know then that this is going to equal 12 over the square root of 9, which is 12 over 3, which is 4. Because we did a limit at infinity and it worked out to be a real number, therefore there is a horizontal asymptote at y equals 4. So now let's look at what happens when x goes to negative infinity in the limit. Once again, if we tried direct substitution, we would get infinity over infinity, which is indeterminate. So we're going to multiply by 1. Because of this square root of x squared in the denominator, that tells us the form of 1 that we are going to use. Now this equals the limit as x goes to negative infinity. In the denominator, these two multiply together, and so hopefully you'll get faster at just seeing that 1 over radical x squared times radical 9x squared plus 1 is going to be the square root of 9 plus 1 over x squared when we distribute this to both terms. Now in the numerator, we have to do some analysis because we have square root of x squared that has to multiply this entire numerator, but this x is not under the radical. So we know that the square root of x squared is just absolute value of x, and because x is going to negative infinity, we know we are going through negative numbers, so then that means that the absolute value of x is going to be negative x. Now we take 1 over negative x and we have to multiply it times both terms in the numerator. So 1 over negative x times 12x is negative 12, and 1 over negative x times a negative 5 is plus 5 over x. Now we can apply the limit, and we see that 5 over x is going to go to 0. 1 over x squared is going to go to 0 because their denominators are going to negative infinity. This becomes negative 12 over the square root of 9, which of course is negative 12 over 3, which is negative 4. Therefore, there is a horizontal asymptote at y equals negative 4. So the important concept to remember when you're working on these limits is that depending on whether you're going to negative infinity or positive infinity will affect how you can simplify the absolute value of x. Because we're going to negative infinity, that means we are using negative numbers, then the absolute value of x here was the opposite of x. In part 3, we're going to practice sketching graphs. In this example, we have to find any roots, intercepts, asymptotes, extrema, points of inflection, and sketch the graph of f of x equals 6 over x squared plus 3. Now, we know that we will find roots by setting f of x equal to 0. Now 6 over x squared plus 3 is never going to equal 0 because no matter what we put in as a value for x, that's not going to turn this numerator into 0. So what that means is that there are no roots or no x-intercepts. Now, to find the y-intercept, we know that we can plug in f of 0, which would be 6 over 0 squared plus 3, which is 2. So that means there is a y-intercept on this graph at 0, 2. Now we can go ahead and put that in on the graph. 0, 2. We know it will have a y-intercept. Let's go back. Now for asymptotes, we could have vertical asymptotes or horizontal asymptotes. For a vertical asymptote, we need the denominator to equal 0, but x squared plus 3 is never going to equal 0, so there are none. For horizontal asymptotes, we have to look at the limits at infinity and negative infinity. The limit as x goes to infinity of 6 over x squared plus 3. Well, if we plug in infinity, we would have 6 over infinity, which of course equals 0. So that tells us that there is a horizontal asymptote at y equals 0. Now we can also look at the limit as x goes to negative infinity of 6 over x squared plus 3. Now if we plug negative infinity into x and then square it, it turns into positive infinity. So we get the same horizontal asymptote from both those limits. Next, we have to find extrema, which means we're going to need the derivative. Now f of x can be written as 6 times the quantity x squared plus 3 to the negative 1. That means when we find the derivative, we can just use the chain rule. Take this exponent, multiply it times 6, so we've got negative 1 times 6 is negative 6. That would be x squared plus 3 to the negative 2. And then, of course, the chain rule tells us that we are going to multiply by 2x. So this becomes negative 12x over x squared plus 3 squared. Now we know to find the extrema, we are going to need to set that equal to 0 or does not exist. We've already talked about this denominator is never going to be 0. Remember, we talked about that up here. So this will never happen. And the numerator is going to be 0 at x equals 0. So this is our only critical number. So we're going to put that onto our sine line graph for f prime. We line up x equals 0, put that on there, and we know the derivative is 0 there. Now we pick a test point over here of negative 1, and if we plug negative 1 into the derivative, the numerator will become positive. The denominator is always positive, so we don't need to plug in. So that means putting a negative 1 in makes the derivative positive, which means f is increasing. Over here, a test point would be positive 1. If we plug positive 1 into the derivative will be negative, which means f is decreasing. Because f is changing over from increasing to decreasing, in other words, the derivative goes from positive to negative, we know that we are going to have a max at x equals 0. Now we already know that f of 0 is equal to 2, so we know that y-intercept is also the relative max at 0, 2. So now we know what that has to look like on the graph. A relative max, we know we have a horizontal tangent there, so that's going to have to look like this. Now we are ready to find the points of inflection. So now we know to do that, we're going to need the second derivative. Now we know f double prime of x. We're going to have to take our first derivative and use the quotient rule. So the derivative of the top is negative 12, and we have to take that times the denominator, x squared plus 3 squared. Then we will subtract the numerator, negative 12x, so that becomes plus 12x, times the derivative of the denominator, which we're going to need the chain rule, so that will be 2 times x squared plus 3 to the 1. Chain rule says times 2x. And then we have to take the denominator, x squared plus 3 squared, and we have to square that. Simplifying, we get negative 12 times x squared plus 3 squared. Now over here, we've got 12x times 2 is 24x, times 2x is going to be 48x squared, and then we have to multiply that times the quantity x squared plus 3. Our denominator is x squared plus 3 to the 4th power. We need to factor. We can pull out a negative 12 and a quantity x squared plus 3. And we would have left from this first term x squared plus 3. Then this plus sign, because we pulled out a negative, is going to have to be a minus sign, so that when we take a negative times a negative, it turns into that positive, and we have 4x squared. And we have x squared plus 3 to the 4th power. Now we've got negative 12 in the numerator. This quantity x squared plus 3 cancels one of those in the denominator, so we have x squared plus 3, that quantity to the third power now. Inside here, we have negative 3x squared plus 3. Let's continue to simplify. We get, now in the numerator, now we've got negative 12. From inside this quantity, we can factor out a negative 3, and we would have left x squared minus 1. We have our denominator, x squared plus 3 cubed. And we can simplify one more time here. The second derivative becomes 36. This quantity will factor into x plus 1, x minus 1, and then the denominator, x squared plus 3 cubed. And we want to know when this is 0 or does not exist. The numerator will be 0 when x is plus and minus 1. The denominator is never 0, so that's never a DNE because this is always positive. So now we know that we have to put x equals negative 1 and x equals positive 1 onto our sign graph for f double prime. And then we have to do test points. Now when we get ready to plug in, notice the 36 is always positive. We don't have to think about it. The denominator is always positive, so we don't have to think about that either. So when we're doing our test points, all we have to do is plug into the quantity x plus 1 times quantity x minus 1. If we pick a test point of negative 2, then we would have a negative times a negative, which is a positive, which means the graph is going to be concave up. In this region, we have a test point of 0, and we would have a positive times a negative, which is negative, so the graph is concave down. Over here we have a test point of 2, so we have a positive times a positive is positive, so it will be concave up. Now the places where the second derivative changes over from positive to negative or negative to positive are going to be points of inflection. So that means we will need to evaluate f of negative 1, which is going to be 6 over negative 1 squared plus 3, which is going to be 6 over 4, which is 3 halves. So we have a point of inflection at negative 1, 3 halves. We also have to plug in f of positive 1, which is going to be 6 over 1 squared plus 3, kind of squeezing it in here, which is 6 over 4, which is also 3 halves. So there will be a point of inflection at positive 1, 3 halves as well. So now we can put those two values onto our graph. So there's a point of inflection at negative 1, 3 halves, and there's a point of inflection at positive 1, 3 halves. we already knew that there was a max here at 0, 2. So now let's look at our combo graph. Remember, on the combo graph, you want to put any x value that appears anywhere on either of the two sine graphs. So we're going to put -1 where there's a point of inflection. We're going to put 0 where we know there's a max. And we're going to put +1 where we know there is another point of inflection. So from -infinity until -1, we can see that the graph is increasing and concave up. So that has to look like this. Now we also have to remember that we have a horizontal asymptote at y equals 0. So let's get that on the graph. Now, when we have that make sense, with knowing that the graph has to be concave up and increasing, that tells us to draw it like this on its way to that point of inflection. We translate this increasing and concave up section right there. And we know as x goes to -infinity, the graph is going to approach y equals 0. And the reason we know that is because this limit told us as x goes to -infinity, the y value is going to approach 0. Now, in this region of the graph, from -1 until 0, we are going to be increasing and concave down. So we know that this portion of the graph will have to look like this, and that actually makes sense with what's going on from the point of inflection to the max. It has to be increasing and concave down. Now, from 0 to 1, we're going to be decreasing and concave down. So that's going to have to look like this. So from the max until the point of inflection, we are decreasing and concave down. That also makes sense with how we have to connect the points. Then from 1 to infinity, we are going to be decreasing and concave up. So that has to look like this. So we go up there to the graph, and now we have a completed graph. We had to be increasing and concave up until we hit that point of inflection. And if I scrunch this down a little more, really we could have drawn this kind of down here, so you might be able to see a little better how they connect in. Before we transferred them up to the main graph. But the combination chart is nice because it gives you the overall view of the whole graph, and then you just have to connect the point of inflection to the max to the point of inflection and include that horizontal asymptote.